a very good place to live in. And this is an aerial view of Karlsruhe. It's a student city and has very vibrant culture of students, and people from various countries are also here. So it's very nice to live in. And then this is the KIT campus north, where we are situated inside a kind of a jungle, but still you ask of any state-of-the-art technology or instrumentation, we have it. And here is the Institute of Nanotechnology, and this is my group, the Han group. It's quite big group, and also my supervisors, Professor Agassi and Ben Brightung, is a group leader. We make. I will tell you what we make in the printed electronics in a moment. So printed electronics. Typically, those who are not so familiar with the topic might think, what can printed electronics achieve? I mean, right now there is so much technology anyway that's going on. The simple answer would be that there will be an emergence of new electronics. This is not a disruptive technology, but a constructive technology. So for example, if you want to make transparent displays or wearable sensors, medical sensors, or for new securities because of some variations, it's all useful in these aspects. And of course, if you want to look at the societal impact, then the Internet of Things and Internet of Energy, which is the next thing, as David said, every person will have about 100 sensors attached to him or her. Then this would definitely be one of the front-end technologies for Internet of Things. And wearable medical devices and soft robotics, as I said. So some of the examples include, like medical glucose sensors or RFID tags. RFID tags are already in the market. For example, Decathlon, they use printed RFIDs already. And in case of the biomedical sensors, we would like to have some non-invasive. That means you don't want to pierce the body and get blood for blood test. Maybe we can use saliva and sweat, etc., for testing our, let's say, blood glucose or human glucose levels, or the salts or anything that is in the body. So for a non-invasive or non-enzymatic sensors, printed electronics is one of the 4 players. Then, as I said before, we are not a disruptive technology, or printed electronics is not a disruptive technology. It is more about adhering onto different functional materials or different substrates such as plastic and paper. And as we start with the electronics, we start off with transistors, diodes, antenna, etc. So if you look at the table here as a comparison, just as a comparison with conventional electronics, the integration density, for example, you want to make within 1 centimeter square, you can have a billion or 10 million transistors when you are looking at conventional electronics. But for printed electronics, you will have it low. And the switching times are, it's rapid. You have gigahertz of frequency in conventional electronics, but it's not so in the printed electronics. However, the huge impact or the huge advantage would be in the fabrication areas. We can print in huge, humongous, large areas in a single go. For example, if you want to make a huge display on, let's say, at the Times Square in New York, we have to assemble different silicon displays. Whereas if we can print it in one single go. So that is the major advantage. But here I would like to say attention. Therefore, printed electronics is complementary to silicon electronics, but not disrupting the technology. So if we are talking about printed electronics, printing means we have to have some solutions. And that means there have to be different deposition methods. So in this case, there are some drop-on demand techniques here, and these are some blanket covering techniques, such as if you have spin coating or dip coating, for example, you dip a substrate. It can be anything. It can be a glass, it can be silicon wafer, it can be your textiles or paper, anything. You can pour the liquid and then spin it so that there is a uniform film formed on it. Or similarly, in the dip coating, when you dip the substrate, there's a uniform film that's formed. However, these don't give you different designs that you want. If you want to make complicated circuits and all, you need to draw them. So for that, there are different drop on demand. These are drop on demand, as in whenever I want to drop the solution, I will on demand I can put it. So these are two examples of it, which I'll be talking in a moment. So for example, slot casting or microplotting, which is available in the Institute of Nanotechnology, we use this to make extremely small resolution films. For example, if you look here, the printed resolution, the drop resolution is about 30 micrometers. Or if you have a look here, these are some conductive silver lines which have a width of 50 microns and length. You can actually draw whatever you want. This is like taking a pen and then drawing on the paper. It's as simple as that. Then to get this microplotter ready, what we do is we have a capillary. I hope you can see the capillary here. So this is a piezoelectric material, and to this we attach a capillary with some glue, and then we give some voltage pulse to the piezoelectric material. That makes the capillary vibrate and then pull out or push out the ink that it has. For example, there is some graphene ink here. When we give certain voltage to this piezoelectric, a piezoelectric is nothing but which gives out some mechanical energy when you give an input of voltage. Then it vibrates and the capillary dispenses the graphene ink. These are two different angles of view when we are printing using the slot casting, which I will show in the next slide. One moment, I am trying to play this. Yeah. So if you, for a human eye, when you are looking at the slot casting machine or the microplotter, which is this, you can see, please have a look here. This is printing the graphene and it has very high resolution, and you can print any kind of structures. In this case, I am trying to print some meander structures for graphene resistors. And this is the camera. So you don't need to worry. You can also have a look at the bigger picture using the camera. So the thing that we are printing here, we would see in the camera as a, this is in the realistic view and this is in the virtual view. So these are the different views for the microplotter. Whereas for the inkjet printer, this is also another drop-on-demand technique, wherein there is another piezoelectric actuator and some inkjet printing head, where you have some ink, whatever ink you want. And of course, the viscosity and surface tension, all these have to be carefully researched upon. And once you have the ink, you can eject the droplet. You can eject the droplet by using this piezoelectric actuator once again. And then once the drops are spread and the solvent is evaporated, you have the dried film. You can make any kind of designs using the inkjet printer as well. So here there are some methods followed to check whether the viscosity of the ink is suitable or not. For example, if you have very high viscosity, it would be very difficult to print. But if you have also very low viscosity, there would be something called satellite drops. That means around this dried film, you would have other islands, which is ideally not wanted by the printing community. Then these are some examples of a printed film. So what I want to show here is, if you look at these drops, what inkjet printing also does is it prints drops, and these coalesce slowly into lines or circles or anything. For example, to give you a view. So in this case, we are using a glass substrate, and then we first check whether the ink viscosity is fine or not, and then we make the printer ready. Now that the ink viscosity is perfect, uh, here I would show this is a cleaning pad wherein if we want to clean the nozzle heads, these nozzles are 20 microns in diameter. So we need to sometimes clean the nozzles, and then we find the area to print. For example, we want to print in this particular area, and then we tell the inkjet printer, we select this area and tell it to print over there. And once we select that, we can print, for example, in this case, indium oxide, aqueous inks of indium oxide. So, oh, sorry. So in this case, we have given the design in the pattern editor. We give the design, or we, in this case, we want a circle, and then we also define the area where the inkjet printer has to print. We checked for the viscosity of the inks, and now it is printing. What it does is it is dropping circular drops in the x direction, and then once one layer is done, it goes into the y direction forward and then prints the next layer, and so on. If you, and then also the layer thickness depends on, of course, the substrate, the solvent, and also many other factors. For example, here the layer thickness is about 150 nanometers, and here we wanted to print a circle, and you can see quite good circular shape. And these, as I told you before, are some satellite drops which arise because of the imperfect viscosities of the ink. So now that we have printed this graphene electrodes using microplotter and also aqueous indium oxide semiconductor using the inkjet printer, the next thing would be to process them. And for this, we can either heat the precursor. The precursor is nothing but a salt solution that we used to make the indium oxide. Or we can also photo anneal them or laser anneal them. This is ultra fast, that's why I call it rapid. This happens in few milliseconds. And then we can also use something called chemical curing for nanoparticles. So in this case, if we are using, instead of a precursor, we use nanoparticles, which is the same material, but uh, the precursor is pre to the indium oxide, and nanoparticle is just the indium oxide nanoparticles. These are two varieties of the same thing. We can use chemical curing to, in order to get a very stable and dense films. Sorry. Yeah, after the semiconductor is printed and processed, we print the electrolyte. This electrolyte helps in activating the device, whatever electronics that we print. It can be a transistor, it can be a capacitor, it can be, later on some circuits. So the electrolyte helps in activating this device that we printed. For example, the underlying thing that it uses is something called an electrical double layer, wherein at the semiconductor or at, at an interface. So if for example, this is a semiconductor and this is the electrolyte, there is an electrical double layer formed here, and this activates the semiconductor. And once the semiconductor is activated, we can make a plethora of circuits. And in order to make this electrolytes, we use, there are a variety of materials that can be used to make electrolytes. In this case, I will show you one of the electrolytes that we use. This is called an ion gel, wherein we add this backbone polymer of PVA and also a PEMA, and there is a solvent, DMSO, and this keeps the DMSO solvent keeps the overall electrolyte quite dilute so that it can be inkjet printed. And once the DMSO is evaporated, so obviously once we put some solvent, the solution, the solvent has to evaporate. And once that is evaporated, the PVA and PEMA cross-link physically because of the drying, and then they turn into a gel-like structure. If you can, sorry about the sound. So in this case, to show you, I wanted to fasten the drying process. So we are um, spinning it, and as the ink is being dried, one can see that the gel is formed. So this gel is acting as electrolyte, and as I told you, the electrical double layer forms, and then it activates the semiconductor. So this is one of the examples. For example, the yellow part is a semiconductor. Uh, Yellow part is a semiconductor, and this is the ion gel that is activating the semiconductor. So where all can we use these? For example, we have a lot of logic circuits that we are making in the Institute of Nanotechnology. For example, when we have something called a transistor and a resistor together, then we can make an inverter, wherein if we give an input voltage of, let's say, from -1 to 1. So as long as the input is lower than certain threshold, then the output is high. You must have known about, definitely know about inverters when, for example, in the electrical power supply and all. So at low supplies, it has a very high output, and then at high supplies, it has a low input. That can be seen in form of a gain. So higher the gain, better the inverter. In this case, we have a gain of 6, which is quite good. But then this has some resistor component. Instead, if we replace the resistor with a transistor component, this can be achieved by playing with some dimensions of the transistor and the active materials in the transistor. And once that has been achieved, then we can get a 5 times increase in the gain. So these are two examples of an inverter logic that has been made in the Institute of Nanotechnology. Why I talk about an inverter is because this is one of the most basic component of an electronic circuit, which I will show here. For example, in any digital circuits, like let's say ring oscillators, a ring oscillator is like it is nothing but with an enable signal, you can turn on the oscillation and turn off the oscillation. That is the basic definition of a ring oscillator. For example, if this enable is at 0, then the ring oscillator is in off mode. Otherwise, this NAND gate, it acts as an inverter, and then the ring oscillator goes into the active mode. So in order to, this schematic helps you in understanding. For example, this is like a 3-stage ring oscillator. So the switching frequency of the ring oscillator is dependent on the number of stages it has. And higher the frequency, better it is. In this case, we have a frequency of about 360 hertz, which is quite good for printed electronics. But if you are thinking of comparing with conventional silicon electronics, which has like gigahertz or megahertz of frequency, this is not comparable. But if you want to look at the front end technology, like the sensors, where you want to measure temperature over for every 1 second, this is the perfect technology for that. And it's easy to make. You can make it on a flexible substrate, you can make it cheap, etc. If I have highlighted this 0.6 volts, because if you look at any energy harvesters or printed batteries, printed energy harvesters that are being made nowadays, there the supply voltage that they can give is also of the orders of less than 0.6 volts. So if you look at ring oscillator here, which means that this would be really the printing process first, and then we have to, of course, we have to do some characterization of the devices, and then from the characterization we model the devices, and from there, and then make the circuit design. This is a ongoing process, and it's a cycle which is, once the design is made, we make the printing again, and then we check with the simulation, and then also correlate, and this goes on for any device or design of the circuit designing. This is called a process design kit, and our group is very electronics. The other stuff that we make are we recently made with one of our colleagues some notes and also some carbon coated. Now we can print real, get very dense films which can actually power the transistors that I was talking about, or the huge capacity. 1800 milliampere hour per gram is very decent for printed electronics, and as I said, we were able to power the ring oscillators. The others are printed antenna. These are printed by, again, our colleagues. I can also, during the question answer session, I can maybe show you them. These are printed on a flexible substrate, and you can bend them to any angle that you want, and they still work quite well. So, I mean, as a summary, I would like to say that the printed electronics is, again, not a disruptive technology, but the is quite high, and we are making digital circuits on these flexible devices using ion gels, and then we are also able to activate them or give the power supply using some printed batteries and antennae. Yeah. So I would like to acknowledge some of these funding institutes and also my supervisors and other colleagues. And this is our Meragame group. And as you can see, this is the new norm for clicking pictures as well. I am happy to answer.
Now, I mean, questions will be at the end of the next talk. So now we will have Mahmoud, who will introduce the printed electronics they are doing at Central Institute. So can you stop the sharing, Surya?
Yeah, 1 second. Yeah.
Perfect. Okay.
Thanks for the introduction, David, and thanks for the very interesting presentation, Surya. So let me just get my screen up. Hope you can all see my screen now, the correct view.
Not yeah. Perfect. Okay,
good. So my name is Mahmoud, and I'm from the University of Southampton. Our group has been working on printed and flexible electronics for a while. And really, the techniques we have been following are very similar to what Surya has presented earlier. So my talk will more focus on applications and the demonstrators we have been looking at, and how we have adapted some of the printing electronics techniques to actually coexist with silicon electronics to get into the gigahertz range, into the scalability, and into the reliability of having full functional electronic systems. So my talk will first go briefly on what printing techniques we have been using at the University of Southampton, what applications we've been looking at, and I'll also introduce you to some of the methods to special when it comes how electronic lithography methods, the deposition and the fabrication methods, and then we applied it to printed electronics using inkjet screen printing and so on to enable zero-cost scalable IoT for large area applications. So how do we actually print our circuits? You've heard a lot about inkjet printing, and this is the exact same printer you have been seeing earlier in Surya's presentation. And as Surya said, it's a thin film, high resolution technique. It does need optimization. You need to go back and look at your ink, your droplet size, and viscosity. But it allows you to print on demand. You don't need to wait before you start doing photolithography. So it's very well suited for prototyping and for very high resolution. And then here is a prototype of a dipole antenna that we have printed on fabrics with inkjet printing. What we use for more scalable manufacturing and mainly for printing on textiles is screen printing, because screen printing allows us to print significantly thicker layers compared to inkjet printing. So one layer of conductive silver from screen printing can be in order of few micrometers as opposed to hundreds of nanometers. Ink layer very quickly and you get your complete system printed. What we have developed in-house, and we also use commercial printers, is direct write printing or dispenser printing, where we use a mechanical nozzle to dispense or squeeze ink onto a large area substrate. So here we have a picture of our large area dispenser printer, which we've used to print electronics on large interactive posters, and also a printer which we use to rapidly prototype PCBs without any optimization or careful ink selection or choices about how we print a circuit. So some examples of what we have been printing or what we have been looking at with printed electronics. One thing is for biomedical application, we have been looking at screen printing functional electrical muscle stimulation electrodes, which go directly on textiles and can help patients in rehabilitation applications. And the other thing we have been extensively looking at has been energy harvesters. So in here we have got a combination of inkjet and spray coated solar cells on textiles. And we've also been printing RF circuits and combining them with conventional silicon-based electronics to realize wireless energy harvesters and wireless communication front ends using different printing techniques. Printed electronics have their limitations. They are not a solution to everyone's problem, and they do require some tuning, they do require optimization. And in this slide, I just have some few examples from the dark side of printing. So I can just get that off. Get rid of that. Just try and okay, that's better. So a couple of examples is that when it comes to like dispenser printing or inkjet printing, you can get non-uniform surfaces, you can get non-uniform thicknesses. If your nozzle is not clean, you could get ink driving through your circuit, connecting circuits that should not be connected in the system. And when it comes to thermal reliability, most conductive inks cannot handle soldering, and even when it comes to pads, they can merge together, or even if you use special high temperature inks, you're really limited on how you can reflow solder them or get them to connect with normal electronics. So one particularly challenging printing surface is textiles. Textiles, as you can see in figure 2 in the SEM cross section, are very rough. And once you have surface roughness and you combine that with a high frequency or AC electronics, then you will have surface roughness, you have skin depth losses, and you have very high resistance, and your application is almost impossible. So we have developed a method of using printable dielectrics to smooth the fabrics and smooth porous substrates and make them more printing friendly. So what we use is we have our fabric substrate, we get a screen printer, we have an open mesh, which doesn't have any geometry, which doesn't have any patterns, and we squeeze our interface, which is a dielectric material, and then we can use it, we can actually tune those dielectric material, dielectric properties. And we have a smooth layers, which, as you can see in the SEM cross section, gives us a nice texture, a nice fabric, which has got less than 10 micrometer surface roughness, which allows us to print our conductive traces directly, reducing the cost and reducing the amount of inks that you need to print to fill the textile holes. And in figure 3, I just have an example of the high frequency losses to make a point that surface roughness is indeed a problem. So if you have a 10 micrometer surface roughness, your 50 dB attenuation in a standard transmission line point can go down by more than 10 gigahertz compared to 1 micrometer roughness. So it's in the interest of everyone to print and work with smooth surfaces. And even with textiles, there are methods to make them more printing friendly. What we came with to avoid some of the problems of printing is what we call hybrid photolithography for low-cost flexible circuits. So we've adapted some of the photolithography methods used in nanofabrication and printed circuit boards to suit flexible circuits. So what we start with is commercially available polyimide substrates, which come with a smooth homogeneous copper layer on top, which we can then etch. And this being an organic substrate, it's lower costs than flame retardants and FR4 PCBs and ceramics. It's more environmentally friendly, and it can be integrated in many applications which require flexible electronics. And it also has better thermal reliability than standard circuits. So we know we can confidently assemble electronics on it. We can solder, and we can use it for standard manufacturing methods. The way we do it in-house for improved throughput is we use a silicon wafer just to stabilize our substrate, to just keep it in place. It could be a glass substrate, it could be any surface which can withstand. We also use alumina tiles, and we adhere our copper clad captain on surface. We spread photoresist, and instead of relying on spin coating, which is usually expensive and only available in clean rooms, we can either print photoresist directly using a standard inkjet printer, or simply paint it or doctor blade it using a roller, using the techniques Surya introduced earlier. Then we get a UV mask, which can be printed using any high resolution plotter, and we expose that to UV light to etch the traces, and we get the developed photoresist, which then has the patterns we have on our photo mask. Using a standard etching tank, which is commercially available and very low cost, we can get our traces, which can be PCBs, antennas, or complete systems. And once that is ready, we can then cut them, and we have our individual component, which we can mount components on this board and then integrate them in complete systems. So what this looks like is we normally have 1 6-inch or 8-inch wafer. You have multiple designs, multiple individual components in this wafer. We etch them individually, and then we cut the entire thing into smaller pieces. We assemble it and integrate it with textiles. We usually use heat pressing or vacuum forming to integrate flexible polyimide circuits into textiles for wearables. And therefore, we can have components or complete systems which can be fabricated using a straightforward method which accommodates multiple designs and allows faster prototyping. So we have used this to build complete systems, and by systems I mean wireless systems with energy storage, computing, and wireless communications based on standard components. So on the left-hand side, we had a demonstrator of a quite complex system which had an energy harvesting front end, a battery, multiple semiconductors and processing capabilities, interfaces to sensors, and finally a bespoke flexible antenna which we have designed. And even though we're doing it on a low-cost organic substrate, we're not trading off the performance. So if you look on the graph, our bespoke antenna in the blue line can transmit over 10 times. When it transmits, you can receive 10 times more power than a standard reference antenna on a PCB because it has higher gain, it's tuned more for a substrate, and it can achieve the same performance as standard electronics. So this was demonstrated for Bluetooth and Wi-Fi applications at 2.4 gigahertz, but frequency for this type of circuits and for these type of substrates is not a limitation. So we have demonstrated the first textile-based millimeter wave 5G energy harvester, which can convert very high frequencies up to 26 gigahertz into DC voltage successfully for energy harvesting application. And the secret is we only have one tiny die standard semiconductor in the system, but everything else is distributed and based on our high resolution, highly reliable fabrication technique. So the whole approach and the whole point of this approach is driven by reliability. And normal electronics, which are based in PCBs, they sit inside a case, they have protection from the elements. Flexible circuits and IoT devices are designed to go anywhere. They can be outdoors for environmental monitoring or in wearables, so they need to withstand bending, be waterproof, and if imagine for a wearable piece of electronics, it needs to withstand machine washing, for example. So what we use, because we have circuits which are very thermally reliable, we use Captain to vacuum form them. We use vacuum form Captain to encapsulate those circuits. So what we start with is a standard strip of Captain. We have our own in-house mold, which is designed based on the size of the integrated circuits we have in our system. And we put the entire system in a vacuum formed oven, and we press the steel mold onto the filaments. And what we end up with is a case that goes on top of the electronic flexible circuits that we developed earlier using photolithography, which can then protect the chips, protect the traces, and make sure it's very mechanically robust. It can be waterproof. It withstands pretty much all industry standard tests. So what we use this for, one demonstrator we had was a reliable long-range UHF RFID antenna. So Surya earlier mentioned the inkjet printed Decathlon RFID tags. So it's also very good for retail for a one-off use application, but they don't really fit the circular economy where you want to track your item from the moment it gets sold throughout its lifetime and all the way until it gets disposed, and then you can find it, recycle it, and figure out what happened to it. But with a filament like this, we have shown that it can withstand hundreds of bending cycles. It can withstand over 30 machine washing cycles. So if you put one of these RFID strips in a piece of clothing or any garment, it can stay there forever. It's fully concealed, and it will maintain its reliability. And then here's the cross section of the structure we looked at in the previous slide, where you have a piece of electronics. The thickest part of the circuit is really the silicon die. You have the adhesive and the top adhesive, which is the molded captain, and then you have the standard polyimide substrate, which is only 25 micrometers thick, so it doesn't really interfere with the wearability of the electronics or how they feel, or even in terms of weight. Now, another application where printing, which is not particularly reliable, which is hard to interface with, can actually be very useful. So we looked extensively at high frequency circuits, and because printing is very fast, printing can be easy to work with, it can be an easy way to prototype electronics before you etch them or before you commit to a scalable design for mass production. When it comes to antennas and high frequency circuits, here in academia and in large scale industries, people use electromagnetic simulators where you build a 3D structure and then you simulate it, you look at the fields, the waves, and you understand exactly how your antenna will behave. If you are in a startup or in a small business, you can't really spend a six-figure number every year on a software license. And simulation is simply out of bounds. Flexible circuit filaments can have better cycle of IoT devices for high frequency applications and give us much more confidence, better than simulation and better than relying on external test facilities or board houses. Yeah, that's it for me.
Which is in the conducting range. Of course, it's not as great as, let's say, a bulk metallic gold, which has 10⁷ Siemens per meter, but this is quite good for quite good conductivity for printed.
Okay, thanks. Then next we have Panagiotis Alivras.
Oh, yeah. Hello. Thank you very much for this webinar. Calling you from the UK, University of Birmingham. Just had a question from Mahmoud from Southampton. You mentioned that printed electronics can, with technique that you described, can actually give you better mechanical reliability. Do you have any, would you be able to comment on the limit of the actual applications that you would be able to use printed electronics, particularly if we talk about industrial processes, transportation, where you can get mechanical loads and accelerations that can go up to a few tens or hundreds of Gs of mechanical acceleration. So we know PCBs have some problems in that, but I'm not sure about the printed electronics.
Yeah, so when it comes to flexible circuits, we have been working with, when it comes to encapsulation, you can always scale the encapsulation for the loads you're expecting. So because we have been targeting wearable or